I see live.
Okay, welcome everybody. This is the Planets Foundation. We're beginning a series of conversations with the movers and shakers in the Breakthrough Foundation. Today we're really pleased and honored to have Pete Klupar from Breakthrough Central in it's Menlo Park.
Menlo Park.
Pete's here. Kevin is here in rainy Maui, and I'm Jeff Kuhn. Also, we may be joined by Svetlana Berdigina, who's off at a meeting trying to understand the interaction of stars with new planets. Hopefully, we can welcome her. Hi,
Hello.
Svetlana. We have a terrible echo. Okay, well, we see you. When you want to chime in, just break off the mute, and we'll try to control the sound and the feedback as we go. So, Pete, we've all heard about the Breakthrough Foundation and its many various efforts to change the world. One of the most exciting is the Starshot and the opportunity of actually sending a probe at speed of light. Almost speed of light velocities to the nearest star. Can you explain for the folks that are just learning about it now what the key points to the plan to get to Alpha Centauri are, and how long it's going to take, and what you think the prospects are?
Okay, so hi, I'm Pete Klupar, and I think the prospects are really good to have send a probe to Alpha Centauri in the next 20 years. I think it's going to take us 20 or 30 years to build the machine to be able to send the probe. And then it'll take 25 years or 20 years for it to get to Alpha Centauri, or I guess now it's called Rigel Kentaurus. How do you say that? Rigel? I guess they changed the name of Alpha Centauri to the Rigel one.
Oh, is that also on the target list? Or is that a name change?
Yeah. It's a name change by the IAU, apparently.
Oh, yeah.
Happened.
Oh, I didn't know that. Why did we change?
Right. I don't know what it is.
Wow.
But anyway, we're going to send a probe, and here I have a mock-up of one of the probes right here. You can almost see it. Maybe if I have to hold something behind.
Oh yeah.
It weighs 370 milligrams, and it has 4 2-megapixel cameras on it, plus a 1-watt laser and and 4 photon thrusters. The whole scheme here is to take one of these star chips and put it onto a sail, and then hit the sail with 100 gigawatts of lasers and propel it for 2 minutes, or give it the energy for 2 minutes. And then after it's been shot at by the laser for 2 minutes, it'll accelerate to 20% the speed of light. And it'll be on its way to Alpha Centauri or Rigel for 20 years, and it'll do an encounter at Rigel. It'll be in system for about a day and a half, and then it'll go out of the system and it'll return to the Earth using the laser, the 1-watt laser. It'll return those images in the next 3 months after that, and then it'll take the light 5 years to get back to the Earth and be received by the same beamer that we used to transmit it out.
So you've already got the Pico craft in your hand. It seems like why 30 years? We're halfway there.
Yeah, well, there's about 30 showstoppers, as we call them, or deal breakers, and we first thought that the spacecraft was going to be the worst, so we started to work on that, and by gosh, we were able to build them. And by the way, those things cost like $75 a piece, so they're not even expensive.
Wow.
Then we thought, well, okay, the real problem is going to be the sail. So we went, because we need to build a sail that is 5 nines reflective and 5 zeros absorptive, which means it's like reflective smoke. And we thought that was impossible. 4 meters by 4 meters, 16 feet by 16 feet, or 15. So 12, sorry. So but then we went out and looked at, started to talk to our friends over at SRI and started to talk to the guys at Vanderbilt and Caltech. And it turns out that people are designing this stuff today, and that people are fabricating teeny tiny little pieces of it right now. And so it turned out that the sail really wasn't the problem. The real problem is what we call the beamer, or what some people call the photon engine, which is to take and combine on the order of 50 to 100 gigawatts of laser energy and get it coherent to within about 1/10 of a wave, and do that reliably every day for a reasonable price. It looks like that's going to be the problem, and that's the top level problem. And there's so many problems associated underneath that, but most of them have to do, or the biggest ones I think today are the coherence, getting the coherence aligned, and then being able to generate or build that many lasers. If we right now, if you buy kilowatt lasers, those are pretty they're pretty available, and they're not very cheap. If they're $100 a watt. If you go to if you go to the solid state or memory, the memory folks that are building CD-ROMs and DVDs and laser discs and those things, they have the cheapest lasers on the planet, and they go for around $1 a watt. The problem is they're at about 50 milliwatts, and you need 2 trillion lasers. You need to combine 2 trillion lasers, and how do you combine coherently 2 trillion lasers to Lambda over 10? It seems like really hard.
So the key words here are, I guess, start cheap and make it scalable then somehow. And okay, so to encapsulate what you just said, is it true then that the thing that keeps you awake at night most in this problem has now evolved to this question of the optical system, both generating the power and then guiding the power to the sail? I thought that the sail technology was not defined, but can you say something about what our friends are doing to make highly reflective broadband reflectors? Are they broadband, or are they single wavelength?
Oh no, they're I think it's 5%. So the stuff that they built at 1500 nanometers, and it's but they have the design tools that allow them to do any frequency, but it's not going to be very broadband. You would have to stack a bunch of them up.
And the mass is okay, at least scalable?
No, it's 5 times too heavy, but it's 5 grams. It's 5 grams.
That's 5 grams. That's still amazing for the whole thing. 5 grams.
5 grams. It's just remarkable. If you just do a web search on perfect reflector, you'll find this stuff. Now, it's also very clever the way they've come up with. So what they do is they first lay down a sheet of silicon, and then they lay down another sheet of silicon dioxide, and then they take a bunch of styrofoam balls, like little teeny tiny styrofoam balls, and they put it over the material. And then they take an ion spray, I forget which ion they're using, and they wash it over the sheet. And what it does is it eats away at the styrofoam balls, and then end up with this surface that's a group of pillars. So it's a series of cylinders that are now stuck to the top of the stuck to the top of the silicon.
So this photonic crystal isn't necessarily being developed for breakthrough. What's the application that's driving the technology now?
PhD thesis.
PhD thesis. Fabulous. And is breakthrough now going to push forward that to make it into so you're into it now. That's amazing.
So really what they do, depending on the size of the diameter of the cylinder and the spacing of the cylinders, you control the reflectivity.
Right.
And I don't know if they, so these guys, it's amazing to me that there's this whole organization of people or groups of people from, like Georgia Tech and Vanderbilt. And, actually, Northrop Grumman is very interested. SRI, which I don't know what the application is, but yeah. So
I have a question, if you can hear me.
Yes, perfect.
When time for your pictures, when you fly by a planet, on that large speed of the craft, would it be pictures smeared, or you have a chance to take very many short exposure pictures?
Yeah, so the fast flyby is a very difficult problem, and because we're moving at 20% the speed of light, it's we're really moving through there. And the advantage we have is that we know when we're going to encounter the planet, and we know where the planet will be, and we know what our speed is relative to the planet. So all we have to do is spin ourselves at the right rate, so that we match our spin rate with our integration time on the planet, so that we can take reasonable pictures. We think it'll take us 2 days to spin the craft up to the speed that we need to rotate at to be able to get blur-free pictures. Now there is some discussion, and maybe Jeff can tell us whether or not these guys are going to be blue shifted, because we're going to be coming at them are they going to be blue shifted by 20%, or what is that going to look like?
Well, it's definitely true that Einstein is not necessarily our friend in this problem, right? And so
yeah.
So, but we'll make him our friend, I'm sure, right? This is exciting news. So one of the 30 technology milestones is sounding like you know the road forward. What are some of the other milestones that are now under your microscope for progress? What do you think is next? The most pressing part of the demonstrations that have to take place?
Well, I think the combining, figuring out how to combine on scale, an infinite number of lasers. I mean, we count, 1 to a few infinity, right? So we're going to have to be. I don't think the difference between 50,000 and a trillion is probably important, but I don't know. Maybe there's a break at every order of magnitude. Maybe it's every couple of order of magnitude. I don't know. We'll have to discover that. The second thing, and that will drive how big the optics are, and how big the mounts are, how big the rest of the approach is. Now, the other extraordinarily difficult problem is how do we, as the craft is moving through space, it's going to collect up a charge, an electric charge. And so an electric particle moving through a magnetic field, translates. So there is a galactic field, magnetic field, but we're not really sure how high or exactly the shape of that field, and we're not really sure how much of a charge the ship is going to gather as it moves through space.
But now it is true still that the are we calling them nanocraft or picocraft? If you're down at 300 milligrams, is that whatever it is? So it still does have. Say again.
Star chip.
Okay. By the way, are these on eBay? Can we buy an interstellar probe just
no, but that's
for our own purposes? I think it's a fabulous idea, especially if it's in the Christmas is coming up. $100. There's a little bit of markup there, but so okay. So this the real, I guess the real question that we're all asking is you've got the scientific community spun up. A lot of brain power is now devoted to taking on each one of these technology challenges. Do you feel like one of the questions I've seen in lots of these problems is, are the human elements of organizing your rowers, moving the craft forward in the sea of uncertainty? Is the human problem now comparable, do you think, to the technical problem in organizing the effort? What's the balance in where all this is going? I remember one of the meetings, you have a huge team of scientists that are involved in this, and there's I guess I felt like all the paddles weren't necessarily synchronized very well in the water.
Yeah, and I would agree that there continuing to be some asynchronous events occurring. And I think it just takes time. I think of a project like a giant, like a 10-meter round sponge ball filled with water. So if you want to run, and it's on a flat plane, if you want to get it moving, you can run as hard as you want and smack into it, and all you do is get wet, right? But if you come up to it and gently start prodding it, and slowly, you can get it to move. And that's kind of where we are right now. We're in the giant sponge ball. But once it starts to move, then we need to influence it in the right direction, and then we can pick up some momentum. The faster we can do that, the better off we are. But I agree, there is a great deal of uncertainty.
Okay, Kevin, you've been quiet.
Yeah, I am still here. One of the questions I think about is, let's assume we get through all these technological problems and we're actually sending these nanocrafts to nearby stars. I would imagine this technology is going to enter other parts of our lives as well. Is there any thought of, I don't know, it seems like if we're at that point where we're sending these things 20% the speed of light, that technology is going to be in other parts of our lives. It's going to, I don't know, transform things. Could you speculate a little bit on that? I don't know.
Yeah. Okay. So since
there's like thoughts of. Sorry. Go ahead.
Since we think about this and discuss this all the time with a bunch of geeks, and frankly, mostly the uber geeks, our minds always revolve around how does it apply to science. Like if you can get a craft going 20% the speed of light, you know, that means that Mars is never more than a day away.
Right.
If you want to go to Jupiter, it's a couple of weeks. You know, so whereas now it's measured in decades. So how do you adjust to research in a world where the travel time to Venus is, you know, measured in days? You can try something, and also they're cheap. They're so cheap. You know, the shot itself to go to Alpha Centauri is about 70K, depending on height. Now,
that's the power cost, right?
Yeah. Well, that's power cost and laser and capex and all those things. So, if you, but it depends on way too many assumptions. But if you think about that, say you could do it for $1 million. Say you could go to Venus for $1 million, and you know, okay, you only get a little bit, a few bits, but compared to the $7 billion or $8 billion JWST, you know, 8,000 million.
Yeah, I think this is really a great advantage, and it will be a great prospect for applications here and solar system, and it has to be used, has to be applied. Definitely, it changes our view on our neighborhood.
And I think you could even decide to go visit the closest star, like the sun. You know, I could imagine that if it were, you know, hundreds of thousands to $1 million per mission, you could come up with all kinds of very interesting things. So I think that's a revolution. Now the harder thing is, and the more significant and more important thing is, well, what about the commercial world, you know, the world that most of the 7 billion people live in? How does that get affected? And I'm not really sure. If the big trick is, well, if we invest in these things, I mean, I don't know, maybe entertainment for the reflective smoke, maybe, and being able to combine this many lasers, I think that it's like asking the boys and girls in 1938, you know, what are they going to do with that stuff they call radar, right? I mean, well, we have some ideas, but you don't get to all the advantages we've done now. So it's hard.
And I think,
do you have any idea?
Well, no, the truth is that, right, all of the major technology advances we would never have predicted as they just emerged. And so, for example, the first one, which is just this highly reflective material. Gee, I want to make a telescope mirror out of that. Come on. I mean, there's all kinds of stuff. And if we could predict it, it probably wouldn't be that special. But the thing that I think we're all excited about out here in the trenches is this possibility of changing the idea of the ecology in this part of the cosmos that we live in. And it's all about transportation of information and ideas and communication. And we just went from the Pony Express to the telegraph, and that's the excitement. So
I think, yes, there will be no limit to creativity with the ideas where and how we can use these devices once we get them in big numbers, and easier way to fly around in the neighborhood.
Okay, so Pete, this has been short, but I think we know that we're going to continue this conversation. I and my colleagues are deeply appreciative of your willingness to share, and we will continue this in this, as we said, this next series. It goes on for the next few weeks. Pete, Thanks much, and we
And
look
you'll
forward.
send me the link to where
Thank
I can
you.
watch myself
Absolutely.
and cringe at all those ums and
No, it's good. It's all good.
all right.
Thanks, everybody.
Thank you.
Bye bye.
Thank you. Yeah.
See you next time.